Welcome to the massive open online course on Aspen Plus. This course will enable one to learn the use of Aspen Plus software for process calculation, process engineering calculation, modeling, and simulation. Before going into the details of this course, let us go through a short preamble which will enable us to understand what is process modeling and simulation in general and how Aspen Plus can be used for this purpose. Let us consider this process plant. Now, this is not actually a full-fledged plant, rather it's a small unit of a large plant. Now I will explain the individual equipment that are present over here. The main equipments in this unit are one distillation column, there is another distillation column over here, there is a pump, there is a small reactor, and there are also an heater, and there is a mixer. So the process feed is passed through this heater and the mixer in series before it is fed into the reactor. The reactor output is then fed into the distillation column. Here the distillate is the product of this unit P1 and the bottom stream of the distillation column 1 is fed into the second distillation column where the distillate is product number 2 of this unit. The bottom stream of the distillation column is then pumped back to the mixer. It is a recycle stream. So basically, the mixer mixes the fresh feed and the recycle stream, and the mixture is then fed into the heater to get heated up, and it is sent to the reactor. Now, in addition to this main equipment, there are plenty of other ancillary equipments and devices such as measuring devices, control system units, there are various pipelines, there are safety devices and alarms, and there are mechanical structure as well which are necessary to build these process units. Now for the time being, these are not important for the focus of our discussion. We pick and choose only these 6 units for our discussion because these are the principal units. Now, we make a schematic of the process plant where we have kept the principal units, that is mixer, the heater, the reactor, distillation unit 1, distillation unit 2, and the pump. These 6 units we have kept. All other things we are not interested about. Now, what happens in this unit of the process plant? We give feed. Feed means the material feed. The feed which is being heated up before it goes to the reactor and the reaction happens. The reactor content is then distilled. That is the feed, material feed. And also we have energy feed. Because we have to operate heater, we have to operate the condensers and the reboilers of the distillation column. We have to operate the pump. We need electrical energy. So basically, in this process plant, we have to give two types of feed. One is material feed, another is energy feed. And the product we will get out of it, this is P1 and this is P2. Two types of products. So ideally, we have to make sure that these products, they are up to the desired standard of their quality and quantity. In other words, we have to make sure that the product rate, the flow rate of the product and its quality is maintained. Now, whatever we have in the process plant, what could be the major tasks of a process engineer out of it? What may be the duties? The first one, we may have to design a new plant. This plant may not be in an existing condition. As a process engineer, we may have to design it for some purpose, and that design can be given to the fabricator for fabrication and then installation. In order to do that, we have to do certain calculations based on some mathematical calculations, or we may have to work with an existing plant of this nature which is there for years together. It might have served us for several years before the market demand has changed the scenario. In the market, nowadays the product quality may be different in demand. So we have to change the product quality. Earlier, say 95% purity might be enough, but nowadays our competitor is selling at the same price a 99% purity. Obviously, then our product will not be sold in the market. In such situation, we have to revamp our process to meet the market demand. So, we have to change a few things. We do not know what to change, but we have to do some what-if analysis. That means, if we change the heater temperature, if we change the condenser pressure, if we change the reboiler ratio, how far the product quality will change? So these are the various what-if analysis that we can do in order to arrive at the market demand quality. Now, these things cannot be done in the real life plant. The plant manager will not allow one to go and meddle with the system. So, one needs to do on pen and paper some calculation. How to do that calculation? We all know we have to replace these processes, or we have to replace this equipment with their mathematical counterpart. Here you see we have replaced the mixer, heater, CSTR, all of them have been replaced by a set of differential and algebraic equations. And these equations have been taken from textbook. They are well-known equations. They have been developed from mass balance, energy balance, rate equations for CSTR, the vapor-liquid equilibrium in case of distillation column, etc. So these are all standard equations whose structures are same. No matter which distillation column you use, they remain same. What changes? The number of trays change in a distillation column. The components change. In one distillation column you may work with methanol, another distillation column you can work with ethanol, and so on. So based on the component that you use, your property database will change. The flow rate, temperature, pressure, those things will change, but the structure of equation remain same. So if your structures are same, you need to feed the data. When you work with mathematical formulation, the real life feed is not of any use. Here you have to use the data. If it is flow rate, then you have to give some information about how many kilomoles per hour or how many kgs per hour, or what is the quality, whether 50 mole percent or 25 weight percent, etc. And also energy data in terms of joule, or for a continuous system it is wattage, joules per second. So these data have to be fed into the process and the calculations can be done. All these equations have to be solved simultaneously. And you know how to solve simultaneous equation. For an example, if you have an equation 3x plus 2y is equal to 5, you cannot solve this equation because you have two unknowns and one equation. So you have degrees of freedom 1. There may be plenty of solutions with pair x and y, but you have to fix either of them. Then the other things will be fixed. But instead, if you have another equation like 5x plus 9y is equal to 11, then obviously you have two equations and two unknowns. You have degrees of freedom 0. That means there will be only one pair of x and y. For this, the system is defined. So the same idea has to be reflected with the entire plant. Here you have to count the number of equations in these units, and you have to see how many variables you have. Accordingly, you have to fix some of the variables as per your requirement, and the process data. They are mostly temperatures, pressures, and inlet conditions, etc. And when the degrees of freedom is 0, it is ready to run the simulation. So all the equations run parallelly, and then the output result comes out of the calculation. Now, this kind of operation 50 years back people used to do on pen and paper because they didn't have any other option. But nowadays, after the advent of computer, people write computer code because that is easier for calculation. But for a complicated system, even writing a computer code is also tedious. For an example, a distillation column, each and every tray they have at least 3 ordinary differential equations. One is for mass balance, one is for component balance, and the third one is for enthalpy balance. And this balance occurs at each and every tray. Suppose a distillation column has 50 trays, then we have to solve 150 parallel ordinary differential equations. Now talk about 2 distillation columns, the number rises to 300. And add on the equations of pump, CSTR, heater, it will be a gigantic task. Now the question is there any other option for easy handling of these equations? The answer is yes. Aspen Plus does it. How? You take the example of this. This is the Aspen Plus window. We will go into the details of window later. We will learn it later in detail, but I will show how it is done. At the bottom, you can see the model palette. Here you have the models of mixer, models of separator, models of heat exchanger, column, reactor, pressure changer, and so on. So what you can do, if you want a mixer, you can simply drag this over here. If you need a heater, just go to the exchanger, bring it over here. If you want a reactor, just go there and CSTR, bring it here. Similarly, bring the columns, distillation column, another distillation column, and lastly we need a pump. So bring the pump over there and there, these are the 6 units you need, and now you have to connect the material stream. So the red things are required. Without them, nothing can happen. The simulation, so this is required, 1 or more material stream. So this is the fresh feed. It is connected with the extensive of product. So this is connected, the pump output, the recycle loop, they are mixed. So mixer output is connected to the heater. The heater output is connected to the reactor. Reactor output is connected to the column. First column output is connected to the second column. The second column output is again connected to the pump. And we have here product 1 and here product 2. Now here you can see the same structure, the model, the unit we have connected. Now each and every module, this is only the front end. The actual calculation happens at the background. So when we are dragging the column, all the equations associated with the column, they are taken into the simulation in the background. We don't see those equations, but those equations are there behind them at the backstage. In the front end, we have this small icon that represents the distillation column. Now, as you understand, in the distillation column you have to set some values. Just look at the values what we need to give. We need to give the number of stages, we need to give the feed stage, we need to give the reflux ratio, and so on. So these are the data we have to feed in, but the background equations we don't bother because they are all set by Aspen Plus. We don't have to pick and choose those equations. So this is how the entire operation works in Aspen Plus. So this is menu driven. It is a designer's delight. Okay, one designer can always add in the this diagram. Okay, and a designer can always add in certain new equipment. He can just disconnect it. Suppose if I want to disconnect, then I have to put right click and then we can cut. Then this vanishes off. This also we can cut and this vanishes off. Instead, we can use some other column. We can use a rad frac column, which is also a distillation column. We can put in here, and then we can connect or reconnect the stream at the destination over here. And then again, we can reconnect. We can reconnect this stream with source, which is here. And finally, this is our product. So when we delete something, then all the equation associated with that particular module, it also vanishes. And when we add in something, then all the equations associated with them, they come in. So that is the beauty of Aspen Plus front end. So this is the flow sheet model. We'll learn it later in detail. So this is how the mathematical formulation can be done. So we talk about the approach to Aspen simulation. Now, just now whatever we had discussed, that is actually sequential modular approach. That means we take some module and that we place them in sequence, and then those unit operation blocks, they are called modules. They are connected and solved in certain sequence for steady state operation. This is called Aspen Plus. But not all the unit operations that are available in chemical engineering or process engineering unit, they may be standard. Like distillation column is standard, reactor is standard, heat exchanger is standard. But there are some equipment which may be non-standard equipment. So you will not find a standardized model in the model palette. For them, you have to write your own customized equation in order to work with. So you have the next one, equation-oriented approach. There you have to work with customized model. Those are developed through equations which are solved simultaneously for dynamic simulation. Here it was steady state, here it is dynamic simulation, and this is called Aspen Custom Modeler. And lastly, there is a combinatorial approach where Aspen Plus is used to initialize the steady state simulation, and the equation oriented approach of Aspen Custom Modeler is used for dynamic simulation, which is Aspen Dynamics. Now in this particular course we have only Aspen Plus. We will discuss Aspen Plus. For Aspen Custom Modeler and Aspen Dynamics, there may be someone may float a different course altogether. So we will limit ourselves with Aspen Plus. So we summarize what we learned in Aspen Plus simulation. What is Aspen Plus simulation? It is about running a specially designed menu-driven computer software in order to quantitatively assess chemical property or the process. Why do we do it? Because we want to predict the flow rate, the composition and physical properties of process streams, operating condition of the process, sizing of equipment while process designing, etc. And finally, how do we do it? We do it by compiling and interconnecting various menu-driven blocks that have underlying physical relationship, that is characteristic equation such as mass balance, enthalpy balance, equilibrium relationship, rate correlation like mass transfer, heat transfer, and reaction kinetics. And these are the advantage of Aspen Plus simulation. It allows various configuration in quick succession, which is a designer's delight. Just a few minutes back I explained how the blocks can be taken out of the flow sheet and how a new block can be inserted. So the person, the designer, doesn't have to pick and choose the equations out of his or her the computer code. He has to just delete certain models or add certain models, and everything is menu driven. So it can be done very quickly, and the simulation also can be done very quickly. As a result, we will have reduced time and effort for new plant design, because you can do faster calculation, you will have more number of solutions to analyze and arrive at the appropriate design calculations. And it answers what if questions that we have already discussed. And it detects optimal process condition within the prevailing constraints. Sometimes the hard constraint comes, like suppose the calculation, it arrives at a 110% valve opening. But in real life, 110% valve opening is not possible. Valve can open only up to 100%, not more than that. But in real life calculation, when we want to do some optimization, this kind of constraints will come into picture and we have to work with them. So debottlenecking, that means identifying those process constraints and alleviate them, that is also possible with Aspen Plus. And last but not the least, this standardization of process is very important. All the common process engineering unit operations are modeled and they are standardized. And not only the model, along with the data for nearly over 1500 pure components. Like if you want to use some common components like nitrogen, oxygen, or some hydrocarbons like methanol, ethanol, or benzene, you do not have to look for their data. the Aspen has option. You can pick the component from its database and attach them. Aspen Plus knows where to bring the data from at what temperature. So you just fix the temperature and pressure and flow rate. Suppose we want to find out the specific heat, which depends only on the temperature. So we have to say the component N pentane at temperature say 300 Kelvin. Aspen will bring the data from its data bank. We do not need to look for the data for that. So it has pure component data. It has over 10,000 vapor liquid equilibrium database. Also it has 3,000 liquid equilibrium binary database. And it has over 60 models of thermodynamics methods like equation of state. We can use Peng-Robinson method, Redlich-Kwong-Swayam method, etc. Those who are very conversant with thermodynamic methods, you know what I am talking about. So these are the advantages of Aspen Plus. Now, to work with Aspen Plus, first we have to understand these basic process modeling features. So we will begin our Aspen Plus training with basic process modeling. We will learn what is the starting page. We have already seen a glimpse of the starting page few minutes back. We know what is, how we will learn how to open a new simulation box, how to open an existing one, what are the extensions, templates, overview. We will be introduced to the physical property environment, setting up the user's universe, method and method assistant. Then we will be introduced to simulation environment and flow sheet. Again, we have seen a few glimpses. Then we will learn how to simulate and get the result. And finally, we will see how to analyze the result. Now, the best way to learn a software is to watch someone using this software. And better way of learning it is to go through a simple example. Now, we talk about a two-phase flash, which is the simplest example that I could think of. Now, first we will learn what is the problem, and then we shall solve the problem in textbook approach. We will take the theory from the textbook, data also from Perry's handbook, and solve it on pen and paper. And later we will do the same thing in Aspen Plus. And then we will see how far the data and the results match. So the problem is something like this. An equimolar stream of N-pentane and N-hexane, equimolar, that means 50-50 mole percent, at 140 degree Fahrenheit and 75 psia, temperature and pressure is given. It is fed to a vessel where it is flashed to 15 psi with vapor and liquid products in the equilibrium at 130 degree Fahrenheit. So you can see both temperature and pressure, they are reduced. So the pressure is maintained at 15 psi, temperature is also maintained at 130 degree Fahrenheit. So one thing is sure, the feed condition is at 140 degree Fahrenheit and outlet condition is at 130 degree Fahrenheit. So these are the different temperature conditions that we have. Now what is to be done? Use Raoult's law. That means it is an ideal system, we have to assume, for the simulation of this system. That is the job that we have. So this is the solution procedure. We have to find flow rates of vapor and liquid. Let us represent it with V and L. The K values of N-pentane and N-hexane. We have to find the mole fractions of N-pentane and N-hexane in vapor phase and liquid phase. So Yp and Xp are for pentane. P represent pentane. So Yp is for N-pentane, Xp is for also for N-pentane in vapor and liquid phases respectively. And as it is a binary system, so 1 minus Yp is N-hexane and 1 minus Xp is N-hexane in vapor and liquid phases. And lastly, we have to calculate the heat duty of the flash operation. Now these are the relevant equation for calculation. The first thing, we have to find the vapor pressure, and we know the Antoine equation is used for finding the vapor pressure, and vapor pressure depends upon the temperature. And here we have an equation, two equations rather, for N-pentane and N-hexane. These are the vapor pressures of pentane and hexane at this temperature. Now we have to use Raoult's law. So what is Raoult's law? This is Raoult's law, where Kp is equal to vapor pressure by the total pressure. And this is also equal to the mole fraction in vapor phase by the mole fraction in liquid phase. So this is for pentane and this is for hexane. So we know P. If we can calculate, we know the temperature 130 degree Fahrenheit, equivalent in Kelvin we have to calculate. So we can understand how to calculate them. So if we know vapor pressure and total pressure is known, we can calculate Kp and Kh. So if we know Kp and Kh, then we have two equations and two unknowns. So we can easily calculate Xp and Yp. So if we know Xp and Yp, then lastly the balance equation, we know everything in these equations except V and L, which can be found out very easily. And next is the heat duty calculation. For heat duty, the relevant equations are, you have to first find out the specific heat. This is the specific heat at temperature T. Specific heat is also a temperature dependent function, and these are taken from Perry's handbook. Similarly, equation for finding enthalpy of vaporization at temperature T and at critical temperature Tc, these are also taken from Perry's. We can calculate all these four. So enthalpy of inlet feed, outlet liquid and outlet vapor against a reference temperature, because we know the enthalpies are always calculated at a certain against a certain reference temperature. So these are the equations for calculating HF, HL and HV, and we all know about this value. Nothing is unknown, so we can calculate them. So heat duty will be the heat out minus the heat in, the enthalpy out minus enthalpy in. So that is the heat duty. So that much heat has to be fed to the flash tank. That is the heat duty. So this is how we calculate. The calculation procedure is like that. So these are the calculation. We have the available data, T in, T out. They have been converted into the SI unit so as pressure P. Now we have to assume two things. One is reference temperature. We can take anything. I have taken 0. It doesn't matter, because in heat duty calculation, if you it is the difference in enthalpy. So reference temperature should be same for all the enthalpy calculation. And the feed, basically in a continuous system, everything is calculated per mole basis. So just for the calculation sake, we have to take a number. So we have taken 1 pound mole per hour, which actually is, in terms of kilomole per second, it stands to be like this. And these are the computed values. Based on them, we have calculated the vapor pressures to be like this. On that basis, we have calculated the K values. On that basis, we have calculated XP and YP. On that basis, we have calculated V and L. And finally, we have found the heat duty to be 1915 watt. Now let us do the same calculation in Aspen Plus. First, we have to fix the components. Now we have two components over here. One is N-pentane, another is N-hexane. So we do not know where to find the N-pentane and N-hexane. So we take the help of this button. Just increase a bit. And here we write pentane and find. Here Aspen Plus will dig out all the components that have remote connection with the word pentane. So just see, we have 1,1,2 trimethyl cyclopentane, 1,1,3 trimethyl cyclopentane, and so on. Here we have 1 chloropentane. So from this list, we have to dig out the one which we are looking for. This is the one that we were looking for. So just press add selected compounds. Here this is added. N-pen01, it has given a component ID which anyway we can change anytime, and this is the component name. C5H10 H12 is the alias. Similarly, we can go for a new search, say hexane. Here again we have to dig out the component. Yes, this is the one that we are looking for. Add. Now we can close it. So these are the two components that we have got, N-pentane and N-hexane. we can change it anytime. Suppose we are not happy with this component ID n pen, so we write pen 10, and here we can write hexen. So instead of penten and hexen, you can give any name. It doesn't matter. It is just an ID. This is the next. I mean, for any Aspen Plus, for that matter, for any simulation, it is always best to go to the next button. Next button, it says that go to the next input sheet needing input. So in many a times we do not know where to go, but next button, if you press, the simulation will take you the point where the next input is required. Now it is asking for the method, base method, that is the property method. Now we know that we have to work with Raoult's law, which is ideal system. So our base method is ideal system. So it is ideal property method, uses both Raoult's law and Henry's law. Just place. Now you can see here there is a icon which is half red and half white. This means that the input is incomplete. The moment input is complete, you will find a blue tick like this. Okay, so the moment I choose ideal, you see a blue tick. That means the input is complete here. Until unless the input is complete, you cannot find this blue tick here. Now our property input is complete. Now we have to go to the simulation database. Now in the simulation, we have to build the flow sheet first. Now in the flow sheet, here we have a single flash tank. Okay, so we have to look for flash. It is available at separator. So this is 2 outlet flash, model flash drums, evaporator, etc. with rigorous vapor liquid or vapor liquid liquid equilibrium. Now our case matches with that. We have 2 outlet flash with vapor liquid equilibrium. Okay. Now we have to add the material stream. So the red means always it is asking for input. So it is asking for 1 input and 2 outputs. So this is the feed. This is the feed input. This is the vapor output, and this is the liquid output. We can rename it. So let us rename it as feed. We can rename it as vapor, and we can rename it as liquid. Again, it is just a simple name. It doesn't have any other significance. Instead of vapor, you can write V also. Instead of liquid, you can write L also. Now, again you press next. It has gone to streams. Streams feed input. Now it is asking for input. So what is the feed condition? So as we know, the feed condition is 50 mole percent N-pentane, 50 mole percent N-hexane, 75 psia pressure and 140 degree Fahrenheit temperature. So here the inputs are all in SI unit, but our data has been given in English unit, British unit. So we change it from metric to English. See, it is asking for English unit. We can mix and match. We can give it in C, we can give it in Kelvin also, but whatever we give, the Aspen Plus software has its own way of converting the unit as it demands. So we give the data 140 degree Fahrenheit and 75 psi pressure, and then the total mole flow rate we have used 1 pound mole per hour. So it is 1 pound mole per hour. Now it is still half red and half white because we have not given the composition. So composition we can give it in mole flow rate or mole fraction, mass fraction, standard volume fraction, etc. We will give it in mole fraction. So pentane is 50%, means 0.5, and hexane is again 0.5. So total is 1. This is the total mole fraction 1. The moment I give 0.5, 0.5, it becomes blue tick. That means the simulation, the input stream specification is complete. Now this is still the block, input block B1, that is the flash. It is asking for input. We can directly go there, or we can just safely press next. It will come to this one. It is always safer to press next rather than going directly over there. Here again, it is asking for temperature and pressure. It is asking for temperature and pressure which are given. Instead of temperature, one can give heat duty. Temperature fixing means we have to supply the heat in such a manner that the temperature is fixed at 130 degree Fahrenheit. Now instead we can say that I will not give more than this much of heat duty. Let the temperature fix, let the block fix its own temperature. So either you can fix temperature or you can fix heat duty, not both. In this case we have to fix our temperature because the problem states like that. So temperature is how much? It is 130 degree Fahrenheit, and pressure is 15 psi. The moment I give it, it is blue ticked. That means all of them now are blue ticked. Okay, so the required input is complete. Okay, required input is complete. Now we press next. There is no input required. It is asking run the simulation now. All the required input is complete. Run the simulation now. You have to say yes. Okay, run it. So it is running the simulation in the background. Basically, it is working with all the set of equations that we have brought in from the model palette to the equation, to the flow sheet. Now we go back to the simulation. You see what happens. These are the loading simulation engine, processing input specification, flow sheet analysis, computation order for the flow sheet. Calculation begins for block 1, flash 2, simulation calculation completed, no warning, no error, generating result. So we have got some results. So go to the result summary. What are the streams? We have 3 streams, and all these streams are given here: feed, liquid, vapor. What are their temperature? See, liquid temperature feed is in liquid phase. What it says, the feed at 140 degree Fahrenheit, it has to be liquid. Vapor phase, vapor, liquid phase, liquid, temperature is 140. So both liquid and vapor, we have 130 degree Fahrenheit, but feed is 140 degree, pressure 75, 15, 15. Now, smaller calculation with substream, mole flow. So how many moles of vapor and liquid we see? 0.63653 pound moles per hour, 0.36347 pound moles per hour. Now let us check with our calculation. Just go back. Here you see, we had calculated V 0.63, here is 0.63653, L 0.37, here 0.37. There will be slight variation in calculation because Aspen may not use the Antoine equation. It has its own data bank which it is using. And what about the mole fraction of pentane? 0.3378 in liquid phase, 0.5953 in vapor phase. So it is almost same. Mole fraction, you see, the mole fraction, pentane, liquid phase 0.33, vapor phase 0.59, 0.33. And lastly, the heat duty. Heat duty we have calculated to be 1915 watt. So let us go back to the block B1. Here some results are given. Heat duty is 6811 British thermal unit per hour. Now if you want to see it in watt, just go there, watt, it is 1996. Our case it was 1915. So 1.9 kilowatt, so it is also 1.9 kilowatt. Now this much of error is evident because we use Antoine's equation, whereas Aspen Plus has its own set of equation and database which is proprietary in nature. They are very much realistic and they are tested on. So that is how we solve it in Aspen Plus, and the results are also matching. So instead of going through this tedious calculation, we can simply put it in Aspen and do the calculation in a very simple manner. Now suppose if you want to change something, if you want to change the feed input from say 75 psi or 140 degree to 150 degree Fahrenheit, then we have to run the simulation once again, and the heat duty will definitely change. Let us see what is the heat duty. Earlier it was 1996, now it is 18.48. So the heat duty has reduced. So this calculation is very fast. A design engineer can perform these calculations very fast and very effectively, but the same calculation if you have to do in this fashion, then it will take long time and sometimes very tedious. So that is the advantage of Aspen Plus. Now with this small introduction, in the next few lectures we will go into the detail of how the Aspen Plus software can be used most effectively. Thank you.